Greetings. In an earlier video I did a comparison of 20 of the cheapest H4 LED headlamps on Amazon. The results varied quite a bit, so I thought I'd do a deeper dive into 10 of them. These 10 have been chosen because they're either broken, or crap, or interesting that they look the same but behave differently, and are crap. First up, the ShuoHui, the one which claimed to have the Qtrednrry LED in the end and was, I think, the dimmest, lousiest bulb on test. I'll desolder these from the back and try and get the thing apart. A bit of teasing and I've managed to get the lens and the front heatsink off, exposing the allegedly Qtrednrry, just because it's on a Qtrednrry circuit board. And these, and I'll desolder this now and check it out and try and work out the circuit diagram. That's it broken into its constituent parts. The bottom board had been superglued into place, well, sort of, as the whole thing was loose. This is a provision for a bridge rectifier for AC use, but that doesn't really make much sense on a H4, as normally they can't be wired the wrong way around unless they're in something unusual like a lantern, unlike single filament bulbs like the H7s. Here's that so-called Qtrednrry LED. What do you reckon? Genuine or just a knockoff? Its board was just sitting loosely in the black metal top ring and connected with one steel wire and one 82 ohm resistor down to the lower boards. It's got a voltage drop of 2.61 volts, at least at the test current used by my transistor tester, so given the 82 ohm resistor it'll be drawing 114 milliamps at 12 volts and 129 milliamps at 13.2. So it's topping out at just a third of a watt, and given the lack of heat sinking, that's probably just as well. The sideboards have triple LED modules, with each triple wired in series and with a 180 ohm current limiter resistor on the back. 2.85 volts drop per LED gives 19 to 26 milliamps through the LEDs. That's 160 to 220 milliwatts give or take per module, 320 to 440 milliwatts per board, or 1.9 to 2.6 watts for all of the side LEDs. At the top one, and I reckon that's 2.2 to 3 watts drawn by the LEDs, and 1.6 to 2 watts just lost by the resistors. Here's the schematic. Each sideboard is a self-contained 12 volt device, which might come in useful for something. As you can see, the difference between dipped and main beam is just a 33 ohm resistor between the two pins. This is about as simple as an LED driver circuit can get. Unfortunately, it's about as inefficient as well, and judging by the way some of the lamps being tested behaved at different voltages, it's probably not the only one to have cheaped out here. Next up is the Muross and the FAVOMOTO, which I have marked with an F on the back. Now there is a difference in the current draw between these two, so I want to pull them both apart and compare. This one has a nice little driver board in it, as does the FAVOMOTO. I'll have to dive into this a little bit more to find out what the differences are. I can see one right there already. Let's take a look. Here are the contents. The little Christmas tree shaped boards weren't bonded to the heatsink, they just had a little metal plate stuck to the front which sort of latched them in the holes on the aluminium surround. The top board is held in place by the tension of its supply wires, which are just soldered through to the square baseboard. Here's the schematic, and this is an interesting design. What you've got is 1.5 bridge rectifiers connected to the supply pins, so no matter which pin is positive and which is negative, it'll rectify it and feed it to the rest of the circuit. However, if either of the outer pins is positive, it also feeds a 1K resistor R3 and engages full beam mode. Basically it means that if the connector plug is wired mirror image, it doesn't matter. Put positive on the middle pin and you're going to get low beam, unless either of the outer pins is positive as well, in which case high beam takes over. This does have the odd quirk that when you ground the middle pin, both the outer pins become high beam pins, and there is no low beam pin. The regulator chip appears to be a H6118A, which is pin compatible with several other regulators of this type, although none of the example schematics show a second resistor to the current sense pin. If it's a high impedance input, I expect that to not really make any difference really, because the potential divider here is R1 and the stack of LEDs. R2 is just taking a tap off it. Anyway, as far as I can see, what it appears to be doing is using R1 and R2 to sense and regulate the current through the LEDs. As the higher the current flow, the lower the voltage at the LED end of R1, so it'll try to keep this constant and bump up the voltage. However, if a supply is presented to R3 as well, this is going to skew that sensing input and drive that voltage being sensed higher. So it'll think there's less current going through, and it'll drive up the voltage to try and counter that. We can test that with the lamp I haven't taken apart yet by putting a variable resistor on the full beam input to see what it does. Here's a 50k resistor. And indeed, as I turn that, it's making the lamp brighter and obviously drawing more power. Next up, the KVSERT, and I wouldn't be surprised if this one has the same driver circuit as we saw in the Muross and FAVOMOTO just now. Let's find out. That's another one in bits. There's compound on the back of the lower board, although I don't think it's heatsink compound. It's probably just some sort of goop. It could be heatsink compound. There's nothing on the top at all, and this actually threads in, so everything is screwed together with the center wires going down through the hole to the base. Here are the boards from both of the KVSERTs, so you can see the front and the back at the same time. The driver is identical to the one in the FAVOMOTO, although the regulator isn't marked this time. This time the LEDs are wired up in pairs rather than in rows of 3. But as it's a constant current switching regulator, that doesn't really matter. Next we have the FRAMZ. This is the one which had the 2 input pins wired the wrong way around. So it's definitely not going to have the same circuit as the previous 3. Probably more like the ShuoHui. Let's find out. Well, it's another simple one, although it does actually have a reverse protection diode in there this time. Back of each board has a pair of 100 ohm resistors for each group of 5 LEDs. And there's a separate one for the top board and a 20 ohm resistor for dip beam. Here's the schematic. And the next one is the Qtrednrry, the one which didn't survive its trip through the post, and then definitely didn't survive being plugged in. Well, I think you can see what burned out. It's a similar design to the FRAMZ, just with more LEDs. It's still got the resistors on the back, which make all those side panels self-contained 12 volt modules. And again, no regulator circuit. Next up is the turn of the DAWEGLOP. This is the one which lasted about 10 minutes before starting to go very dim and flickery on low beam. So I know the board inside is screwed in, but this doesn't unscrew. As far as I can tell, this is some sort of friction fit. And indeed it is. A little bit of aluminium meshing, and the lens comes off to reveal that board and a driver somewhere in behind that. Well, that was fun to decipher. Diodes everywhere, even without the bridge rectifier. Each half of the LED module has 12 LEDs in parallel, connected in series with another 12 LEDs in parallel. At least I assume that's the case, as on the knackered yellow side there are some LEDs which can be lit without their series counterpart working, so it's either failed short circuit or there's a common rail joining all the midpoints together. We can see this if I run them on a current limited power supply. The driver module has another bridge plus 2 diodes to form a 6 diode 3 input bridge, as we saw earlier on the dual bridge modules. It's also got 2 more, D5 and D7, to kick out a supply that's only present in high beam mode. That then goes to a 62k resistor, but if the low input is grounded, D6 will shunt it back down and block the high beam option. Otherwise it will carry on through D4 and turn on MOSFET Q1, which enables the high beam. The low beam MOSFET Q2 will be turned on via a 100k resistor if low beam is enabled, unless high beam is turned on as well, in which case Q1 will pull Q2's gate down and hold it off. Compare that with the other dual colour projector lamp I previously tested, which lights both in high beam mode. Below all this is U1, an LN2576CCT, 2 amp maximum, constant current driver with an operating voltage range from 8 to 100 volts. Next to be taken apart is the Trintion, or HOW. Now this is the one which arrived first of all, and is the one I knackered up to high beam setting by connecting it in reverse polarity. So it'll be interesting, if possible, to see what's actually gone wrong with this one. That's not much of a driver circuit. It's another simple resistor circuit with a diode to ensure that if low beam is selected, one LED bank turns on, but if high beam is selected, both turn on. What I think went wrong suggests that the wiring on my lantern isn't what I thought it was. It actually had ground connected to the low beam pin, not the high beam pin. Switching on the lantern caused the diode to short out a lead acid battery, which never ends well. That made it fail and start conducting in both directions. The next thing to fail then was the connecting wire to the high beam pin, which melted just like a fuse. The shorted diode is why the low beam pin from there on was lighting both panels, and the melted wire is why the high beam pin didn't do anything. Next up, the OmeHoin, another example where nothing's actually attached to the heatsink. We've seen that board before. No, have we? No, we haven't. Here's a close-up of the boards. Unfortunately, I've been unable to find any details regarding that driver chip, nor have I found any other driver chips using a close enough pinout to make any sense. So that leaves us with a schematic that's somewhat lacking compared to some of the others. As far as I can see, I've not missed any connections out, but with no datasheet, it's hard to do any sanity checking on it. Oh well. Time for the final lamp to be ripped to bits, and it's the Xmiral that decided to keel over as soon as I tested it in the car. That was just held on with heatsink compound and obviously the screw, so that brings the connection right out. And there we go, the only one being checked out that's actually an all-in-one design. Well, technically all in two because the LED board is soldered directly onto it, but you know what I mean. Here's a close-up of the top and bottom of the board. As you can see, both LED arrays are 3x4 this time. And here's the schematic. Not so many diodes this time, as this one's not designed for mixed polarity. D1 and D2 just prevent reverse polarity and ensure the circuit gets a supply whether on low or high beam mode. The driver circuit is based on an LN2544 and normally just drives the low beam LED array. If the high beam input is used though, this biases up the chip's DIMM pin with a 100k resistor and also turns Q1 on to enable the high beam LED array as well. Now after probing the board to work out the schematic, I realised that all the components appear to be fine. So what caused the fault? Are the LED panels dead? Actually, no. The LED panels are fine and it looks like it was just a broken solder joint on the negative lamp pin. As you can see, I've managed to reassemble it and it's working fine. All the way up to 60 volts. So I got a handful of useful little LED driver boards anyway. Not to mention a load of potentially useful LED boards themselves. Hope you found that an interesting little follow-up to my earlier video. Thanks for watching.